Hello and welcome to a very special program. This is a program which has been co-sponsored by Teamwork Arts and BIRAC, and it is a great pleasure for us at NDTV to be a part of this. The Indian Space Research Organization, ISRO, is one of the most aspirational organizations in the country. It's an organization that fuels ideas, it fuels ambition, it fuels frugal engineering, and it fuels the hopes of a billion plus in so many ways. Who would have thought, even a few decades back, that India would today be in a situation where we are looking at a space station of our own, where we are looking at Indians being on the surface of the moon in the years to come. There has been a jump in the engineering prowess of ISRO, of profound scientific achievement as well, and the road ahead seems clear based on the ability of some remarkable engineers and scientists. And we've got three wonderful mission leaders associated with three spectacular programs on the stage with us today. Dr. P. Veeramuthuvel is the project director for Chandrayaan 3, very much the man in charge of key aspects of the mission which resulted in the Chandrayaan 3 mission and the Vikram lander touching down on the surface of the moon. Thank you, sir, very much for being with us. Next to him, Dr. Sankarasubramanian K is a principal scientist and group head of the Space Astronomy Group. There is a wonderful spacecraft called Aditya, which is deployed at what is called the Lagrange point, which is doing some fairly profound studies of the sun as we speak. What is Aditya all about? We'll be talking to him about some of the instruments on board and some of the data that India hopes to collect. And Imtiaz is the director of the Directorate of Human Space Flight Program, one of the most exciting programs that ISRO has. It's the Gaganyaan program to have a crewed mission in space in a very finite period of time. And that's just the start. What happens next? Well, perhaps Imtiaz would let us know more about that later. But I'd like to come to you, Dr. Veeramuthuvel, first. The 19 minutes of horror, that's what it was, right? The moment when the Vikram lander started descending onto the surface of the moon, fully automated, at mission control, you could just sit back and watch, right? What was that 19 minutes like?
So as you said, it's an autonomous landing sequencer. We call it as ALS. Once we invoke that ALS, it's like it will take us to landing. So we built all the intelligence. It has to take a real-time decision. Absolutely no ground intervention is involved. So whatever the systems we carried, so there are many systems, critical systems, which has to lead to a successful, safe and soft landing. So one is, in moon there is no atmosphere. So we have to use active control propulsion system, bipropellant system, which will kill the velocity of orbital velocity from 1.68 kilometer per second to nearly 0 meter per second to the targeted landing site coordinates, which means we have supporting systems like sensors. Since there is no GPS in moon, we have to have terrain relative navigation sensors. We had a host of sensors which will give the 6 state vectors information, that is position x, y, z, and x dot, y dot, z dot velocities. For that, we have built many instruments which will provide altimeters, velocity sensors, and inertial sensors. Then we have to have a navigation system. Then we need to have guidance and control system. So all these systems has to work in unison for this 19 minutes. So we were actually, every second, we were thinking that how the systems are going to perform. And this time we have made sure that many multiple mission parts we have put in, like even one sensor failure, how to handle that failure, still we have to have a landing. So like that we built many multiple mission parts. Say any system we will make it for some dispersion bounds. We call it as a 3 sigma dispersion bounds. This time we handle that beyond 3 sigma bounds also. Even all the parameters are going positive sense or negative sense. Still we wanted to have a landing. So we built that kind of preparation this time to have an autonomous landing. So every second was important for us. And finally we got a very nominal result which has taken the nominal path of landing. So we were just away by the landing target coordinates, even though our landing site is 4 kilometer in along range and 2.4 kilometer in across range. We just targeted the center point of that 4 by 2.4 kilometer. We were away by approximately 300 meters.
Right. But you didn't quite answer my question. What was going through your mind at that stage? Were you worried? Were you scared? Were you tense? Because this is the beauty of talking to scientists and engineers. They are so busy with the data and the entire process that the human factor they sometimes don't express. Were you nervous? No, give us the truth.
So personally, I was looking for that crossing that 11.2 minutes. In Chandrayaan 2, we really had the same autonomous landing sequencer. 11.2 minutes, we got the deviation.
Right.
Exactly, we deviated the path. We were having multiple observations, and which led to a crash landing. So I was personally looking after that 11.2 minutes crossing, and the subsequent phases, that is camera coasting, attitude hold phase, fine braking phase, and the last phase, that is vertical hovering phase, wherein we have to operate lander hazard detection and avoidance camera, which has to avoid the obstacles. See, even though the terrain is 4 kilometer by 2.4 kilometer, our landing strip, our landing landercraft size is around 4.5 meter in diameter. So we need to have a obstacle-free landing zone.
Sure.
For us to avoid the toppling. See, we call it something like a stability.
Sure.
When we at the time of landing, it has to absorb the strength as well as it has to offer the stability. So we will look for, like any car also has got a ground clearance. In the road, if any bumps or bounces are there, if it is a long, big boulder is there, it may topple. So similar way, below the landercraft also, we have an engine. Below that, we specified some limit of 320 boulder height it can tolerate. So we already, a priori to launch, we have stored the image, and we take an image real time. It will compare with respect to the onboard image, and it will avoid the obstacle. So that phase also is important. So we were looking for every second how it is going, and finally we avoided the obstacle, and we had that 24 meter by 24 meter safe pocket, wherein this 5 meter is good enough for the landing. So after the touchdown, we got exactly nearly 1.1 meter per second vertical velocity, and it was upright. The lander was upright, and soon after the landing, we could establish the RF communication also. So that ensures that we have successfully landed.
That was absolutely, and I watched every moment of it. I think everybody over here did. That was a fantastic moment when we got to the surface of the moon. But Dr. Sankarasubramanian K, let me ask you this. The Aditya spacecraft is an elegant spacecraft. It's a large spacecraft in that sense, and it's not a satellite, as we have in orbit of the Earth or in orbit of the Moon. It's larger. It is what makes it unique as a space observatory?
Yeah, I mean, first of all, let me thank the organizers as well as you for hosting us. Aditya is, we call it as an observatory. Why it is called as an observatory is it doesn't carry only one payload. It is going to carry about 7 payloads. I mean, it is carrying 7 payloads with it. An observatory is an observatory. It's because it is going to study the entire processes which is happening on the sun to a much greater detail than a single instruments. So that's why it's called as observatory. And if you go back to ISRO with respect to AstroSat, we had an observatory class mission called AstroSat, which is still operating, provides great amount of data looking at the stars. Mm-hmm. Sun is our own star. So studying sun, I mean, of course, AstroSat cannot look at the sun because of its such a bright objects. Sun is a bright object because it's near to us. We cannot turn the AstroSat to look at the sun because the instruments are not designed to look at very bright objects for AstroSat. So Aditya L1 is going to be similar to an observatory class mission like AstroSat, and provides us an important information which is currently not available from any of the international missions. So since it carries multiple missions looking at the same object in multi-wavelength band, it gives us an unique data, which is why we call this an observatory class mission.
And what is it that we're looking out for?
Okay, so as I said, the sun is our own star, and it's not it doesn't stand still. Though every day morning we see the sun and then it sets in the evening, the sun also goes through a lot of dynamical processes. We call that, many times you would have heard about the term called coronal mass ejections and solar flares. Right. These two are very dynamical systems where, for example, solar flares gives you a lot of high energy photons. The photons is, if you look at the electromagnetic spectra, what we see from the sun is the visible part, but sun is not only seen in the visible, it also seen in other waveband like radio in the lower energy band, and in the higher energy band in X-rays and gamma rays. So when solar flare happens, some of these high energy particles, high energy photons, which is emitted in the X-ray bands, and that can interact with the Earth's atmosphere and changes the ionospheric compositions of the Earth. And we also have this coronal mass ejections. It's not only the photons, it also throws out a lot of high energy particles like protons, electrons, and heavier ions, even ionized ions is thrown into the interstellar medium. They also can interact with some of the Earth's magnetosphere and funnel down to the Earth's north and southern poles. And that's how we see these auroras borealis and auroras australis. And you would have seen, I think, a week before, not even a week before, a few days before, you would have seen a very fantastic aurora created by coronal mass ejections, which happened somewhere around 29th or 30th of November.
Yes.
So Aditya is going to look at these informations. It is going to capture the coronal mass ejections as when happens on the sun. And it is also going to study the particles as it reaches the L1 Lagrangian point. So we'll have a connection between the sun and the Earth and sitting in front of the Earth. So sure. Aditya carries payloads which covers these aspects of it.
Yeah. Imtiaz Ali, Gaganyaan is perhaps one of the most talked about themes in this country at this stage. When are we going to get an Indian human space flight through Gaganyaan? When? What does it look like?
Thank you, Vishnu. So, first of all, yes, as far as Gaganyaan is concerned, the objective of Gaganyaan is to demonstrate the human spaceflight capability to low Earth orbit and bring them back safely to Earth. Now, we just had the first flight testing, that's a test vehicle flight on October 21st, and it tested one of the most important things for crew safety, and that was the crew escape system and the parachute-based deceleration system. Now, having done that, there will be series of other tests. So the test vehicle itself, you will have for different conditions of off-nominal situations or abort conditions, you will need to test them. There will also be a pad abort test. There will be some integrated airdrop tests. And before actually going to the manned mission, which we are all eagerly waiting for, there have to be at least 2 unmanned missions in identical configuration as the manned mission. Now, it is important to have these unmanned missions because unlike any other mission, as far as a human spaceflight mission is concerned, safety is of utmost importance. So for that reason, you need to demonstrate the entire mission end-to-end with everything identical as the manned mission. Now, what we are expecting is the first unmanned mission should, which is sort of an experimental mission, should most likely take place in the second half of next year. And then subsequently, we will have further unmanned missions followed by the crewed mission. So I'm not really giving a timeline for the manned mission, but this is how things will shape up.
Sure.
Thank you.
Who are India's astronauts? I know that ultimately we may not call them astronauts, and I know you won't tell me what we're going to call them, even though I suspect you know what they will be called. But who are they? And tell us a little bit about them.
So the first batch of Indian astronauts are test pilots from Indian Air Force. And of course, test pilots, by definition, it means that they've undergone a stringent selection process to reach that. And even from the pool of test pilots that were offered by Indian Air Force, there was again a selection process of medical testing, fitness evaluations, and finally 4 of them were shortlisted. So they are there with us. They've already undergone their generic spaceflight training in Russia, which included sort of zero gravity training as well and different courses that were required. After that, they are there with ISRO, and they have undergone sort of mission-specific training, mostly related to the launch vehicles, the spacecraft, the onboard systems, and now we are at a stage that we got to train them on simulators. So when you talk about astronauts, there are essential things like, of course, you should be medically fit. Then you have physical fitness criteria to be followed. Then you have basic intelligence level, your alertness, and then there is skills. So the skills get tested on the simulators. So this is where we stand today, and I think in the course of time that we get ready with the missions, they will be getting trained on the simulators as well.
Dr. Veeramuthuvel, I find it really interesting that the Chandrayaan 3 mission isn't quite over because the propulsion module, and correct me if I'm wrong, you've had it fly back to Earth orbit. How did you manage to do that? There was evidently enough fuel on board. And why is it that you've done this?
The main purpose of propulsion module is to carry the lander to the final lunar orbit. See, the launch, you might be knowing, the launch has taken place and injected both propulsion module and lander at the GTO orbit, that is Geo Transfer Orbit, which is 36,500 kilometers from the Earth's surface. And the propulsion module was primarily used to increase the apogee height to 4 lakh kilometers, which is the moon's orbit, and acquiring the moon further elliptical orbit to circular orbit. Everything was done by propulsion module. And on August 17th, we separated the lander from the propulsion module, and both were on its own journey. Lander has separated and it has remained in that orbit for four days, and finally power descent has happened, which has taken the lander to the surface. Propulsion module was intended only for the main purpose of taking the lander. But still, as a value addition, we have put one scientific payload, which is called SHAPE, which will look at the Earth, and we will be measuring, we will be seeing that we know that it's an habitable planet. So this is again a demonstration purpose. We have introduced this payload. It's a technology demonstration payload. So once we know that this is the kind of a spectral signature it is coming from observing from the moon's orbit to Earth, we can use this payload for the future missions, and we can look at Earth too. Right. Like in some other exoplanets, we can look at it. So from that point of view, this was put, and the basic objective was for 3 months. So we had enough fuel based on the launch vehicle, precise injection by the launch vehicle, and also precise mission management. We got some extra fuel. So we thought we will actually utilize, and we can come back to Earth. And we also tried this experiment to demonstrate for the future sample return mission. Like, for example, for sample return mission and so on, we have to bring the sample back to the Earth. Sure. For that, we have to come out of the moon and come to the Earth orbit. So that is something we demonstrated. Even you would have seen in the lander also. Just before the end of the mission, we did a hop-on experiment.
Yes.
We elevated from the same engine what was descended. We operated that engine. Slightly we elevated by about 40 centimeter, and laterally we moved by 40 centimeter, and we again deployed back the payloads, the scientific instruments. We got a new location, by the way. Yeah. And this was phenomenal, because this is something our chairman ISRO and director URSC was pushing our team to do this particular experiment, which was not part of our plan at all. But we did it in 24 hours. We reprogrammed that navigation guidance and control. We prepared ourselves to do that experiment. That also was for demonstration for a future sample return mission.
Sure. And you deployed Pragyan, the rover, effectively in another location.
No, Pragyan rover was outside.
Okay, so it stayed outside.
The ramp, which is,
the
rover has come out of the ramp. Yeah. The ramp was closed back during the liftoff, and again it was deployed back.
Sure. Tell us a little bit about the Pragyan rover. The fact that it was able to semi-autonomously avoid areas that you wanted it to avoid. There was also a lot of data it generated. What is some of the science that you got out of Pragyan and Vikram?
So the rover, as you told, it is a semi-autonomous way of operation, because a rover is not directly communicating with Earth. It is always communicating via lander, because it is very tiny, which is 26 kg of mass with small size. But it is inbuilt with all the functions. Like, we have to move from point A to point B. For us to do that, we have like how we have two eyes, we had two navigation camera, which will look at ahead of the rover, and those images will be downloaded to ground through lander, and we do a path planning. Another 5 meters, we will move from point A. Then when we go and park there, we have two scientific instruments. One is alpha particle X-ray spectrometer, The next instrument is laser-based induced spectroscopy. These both instruments will measure the major and minor rock-forming elements, like various elements like calcium, iron, titanium, and it has detected various elements also like sulfur and all. So one operates using an X-ray fluorescent technique. We have curium-244, which illuminate the surface of the moon, and by which we can detect the minerals. The other one is basically operates in the laser wavelength, 1550 nanometer wavelength, which is again a spectroscopic kind of an experiment that also measures the various rock forming elements. This will be very complementary in nature. Like Chandrayaan-2, we had a remote sensing payload. Chandrayaan-2 orbiter, which is orbiting around the moon, we had some scientific instruments. This will confirm the actual surface experiments.
Would it help us get an idea ultimately of how much water there is on the moon? Chandrayaan-1 detected particles of water. Are we any closer now, based on the instruments we have, to getting an idea of how substantive that is?
So right now, we got some plethora of science data. The analysis is going on, but right now we have not seen anything that kind of a signature, the area in which where we landed. But however, there are plenty of data we got. I didn't tell about the lander. Lander also has got 3 scientific instruments. One is the seismic activity, wherein we call it as an instrument for lunar seismic activity. We drop that payload onto the surface, which measures the natural as well as artificial seismic activity. So we got one natural seismic activity also, we are looking into it. But several artificial seismic activity it has observed, like basically the rover movement, the payload deployments, such things it has captured. The next instrument, there is a probe which is inserted into the lunar regolith for about 140 mm. For every 10 mm, we add a temperature sensor. Likewise, 10 sensors were there, which measures the temperature and thermal conductivity. So we got a lot of vertical gradient of temperature. Then another instrument is the lunar surface plasma experiment. This is first of its kind. All these instruments are first of its kind. It's a state-of-the-art instrument which is developed in 2 kg mass, 3 kg mass with a very less power. And first of all, that location itself is totally new. No one has gone so far, the location where we landed. And it measured electron temperature and electron density over time. So we got a lot of data, but we will come up with a lot of publications and so on.
In the time. Dr. Sankarasubramanian, who's developed the sensors on board Aditya? Could you tell us about your sub-teams? Are they young engineers? Are they across the country? Is it outside ISRO as well? Because the heart of the Aditya Space Observatory are the sensors on board. Who's developed them?
Okay. So as I said, Aditya carries 7 payloads. 4 of them are remote sensing, and 3 of them are in situ. When I say in situ, it is just measuring what is happening near to the spacecraft. In the 4 remote sensing payload, 2 of them from outside of ISRO. These 2 are big payloads. One is called, we call this as a visible emission line coronagraph. It's a coronagraph which occults the sun. Many of you would have seen eclipses, which is a natural phenomenon, which you get a natural eclipse. Whereas in Aditya, we have a coronagraph which does an artificial eclipse, blocks the disk light, and sees the corona. And this instrument was developed by Indigenous of Astrophysics in Bangalore. And they have a heritage of developing space instruments. In AstroSat also, they had one instrument on board AstroSat. Of course, ISRO helps them with a lot of hardware developments, because one of the important heart of this particular instrument is a very highly polished mirror, which is done at one of the laboratories in ISRO. And similarly, the detector systems is developed at Space Applications Center for this particular mission. Of course, the conceptualization and putting them instruments together and other stuff is done by Indian Institute of Astrophysics. The second largest payload on Aditya is the SOOT instrument, Solar Ultraviolet Imaging Telescope, which images the sun in the near ultraviolet band. And it's an important band because the near ultraviolet, the dynamical variations of the sun is much higher compared to the visible. And they straight away affect our ionosphere. So the variations in the SOOT instruments, the variability is linked to the Earth's system. And this instrument was developed by Inter-University Center for Astronomy and Astrophysics, IUCA, Pune. They are the lead instruments. Again, ISRO helped them with the development of the mirror from one of the laboratory. And also the detector system electronics is developed in URO Satellite Center. And they were putting them together. And this is UV payloads are always a very difficult payload to develop because they are prone to contamination. Any small molecular contaminations can damage the instrument. Right. So we have to develop facilities on ground, which is very clean, both from particulate point of view as well as molecular contamination point of view. So that the facilities was developed in URO Satellite Center, and it's all integrated at the URO Satellite Center.
Fantastic.
And of course, these are all done by, since these are all institutes are involved, there are a lot of young people who goes through their PhD programs, research programs. They learn the tricks with the help of the senior members, and this helps them to develop their career in the space arena. Sure. And two other payloads are inbuilt in URO Satellite Center, which looks at the X-ray wavelength band to look at the solar flares in the remote sensing mode, which looks at the sun as a star and looks at how the X-ray emission from the sun varies with the time.
Right.
And this has an important information about the increase in the temperatures when the solar flare happens on the sun, as well as the particle which is spewed out from the sun during some of the solar flares and coronal mass ejections. And the three in situ payloads, which looks at the particle as it comes towards the Earth, and also the magnetic field tied up along with the particles.
Fascinating.
And these three instruments, one of them is developed by Physical Research Laboratory in Ahmedabad, and the PAPA instruments, which is developed at SPL, Space Physics Laboratory in VSSC, and the magnetometer is developed at Laboratory for Electro-Optics Systems.
Right. It's an entire ecosystem that has been built up over a period of time. We're running short on time. I just wanted to ask Imtiaz a quick couple of questions. What will an Indian space station look like? What would it do?
So, in a way, I think whatever we are talking about, like what Veeramuthuvel has said and what Shankar has said, I think the ultimate aim would be to integrate all this together. So, you will need to develop several technologies. You will need to develop rendezvous, docking technologies, habitats. So, for the habitat, there will be a requirement of environment control and life support systems and various other modules to be able to be there. Now, so far, what we are thinking about in terms of international Indian space station is, of course, Gaganyaan itself will have follow-on missions for various durations and for various objectives. And finally, when we reach a stage where we are able to integrate all this together, I think it will be a sort of small space station, something like 20 to 25 tons kind of space station, wherein there will be a habitable compartment for the crew, there will be a power module, a propulsion module, and there will be a docking port where the modules can come and bring in cargo and crew and attach itself. Of course, it has to have solar panels and radiators and things like that. So we are also thinking that it should be a combination of metallic and inflatable kind of system. So it will be an integrated form of all this when we reach there.
And of course, the ultimate goal is to get to the moon with a crewed mission. I won't use the word manned mission because it could be a woman as well. And this is something that's an absolute national priority. ISRO is full of extraordinary women engineers and scientists, and we would likely have at some stage women on the moon as well, women in Gaganyaan as well. 2047 sounds a long time away, but in terms of the engineering and the science, it just seems like tomorrow, right? Is it very challenging?
It's very, very challenging to have by 2040, if we have to have Indian astronaut on moon, we have to develop many, many technologies.
But it's been wonderful talking deep science with these three gentlemen. It's not something we often get a chance to do. ISRO certainly triggers so many emotions of pride and nationalism, patriotism in our country. But I think behind all of that is some fantastic frugal engineering. It's designed and developed to an Indian model, an Indian ambition, with a future which is distinctly what we want it to be. Over a period of time, this has worked very neatly into our national program of Atmanirbharta, in other words, self-reliance. And going forward, we will have this mark of ISRO really define our space programs and indeed work closely with space programs from around the world, because that's also a key aspect of all of this. Thank you all very much for being with us. All of you remain incredible inspirations, and all the scientists who work with you.